Okay. We're gonna just go a half hour anyway, so good. We'll see you tomorrow then. We're all the Texas people invited.
Actually, Franco studied in Colorado.
Yeah, I know, he told me, yeah.
I don't think there are.
Hmm?
I don't think there are any
No Texas?
students.
No. I used to teach this when I was at Colorado School of Mines, yeah. One of the great in sequence stratigraphy was a professor there, Bob Weinberg, his name. He's retired now, but he was one of the early guys. Besides, yeah, he wasn't with the Exxon group, but he picked up on that and did a lot of really good work convincing people who lived in the Rocky Mountains to use sequence stratigraphy in their exploration. He was instrumental in that. So Colorado School of Mines had a long history of using sequence stratigraphy. Okay, so I'll go on. So here's your maximum flooding surface, the green arrow or the green line. And if you were to drill a well now, let's drill a well down around in this area here. And what is our well log going to look like? Well, it might look something like this. What do you got here? You've got some incised valley fill at the bottom, usually good reservoir. And it gets shalier and shalier as the shoreline is moving landward. You're getting deeper water at any one spot. So you're getting finer and finer grained sediment. And then at this point, the maximum landward extent of the shoreline, you start to turn around and you start to get coarser and coarser grain. That would be like your shoreline sands here, your progradational shoreline sands. If you do, let's drill another well. Let's do one here. And this is what you might get. Okay, now you've got 3 sands, whereas here you had 2 sands. We've got the full incised valley here. We've got some shoreline sands, transgressive shoreline sands. And then we've got a little bit of a high stand sandstone, a little meandering river type sandstone deposit up there. So in this well we have 3 sands. Let's drill one more well. Drill that well here. What are you going to get there? You've got some incised valley here, the little teeny edge of a sand that you caught there. Here's your condensed section, the maximum flooding surface, and then you've got some sand there. So you've got 3 sands there, 3 of different thickness, 3 sands here, 3 and 2 there. How are you going to correlate those? Remember, I've drawn in the correlation, but if you just had those logs, with nothing else to go by, how are you going to correlate? What would you use as a correlation marker? I'll tell you what a lot of people use. They use the top of the sand for correlation. Actually, that's not good because your sand can vary in thickness and so on over an area. Your best correlation marker is to find your maximum flooding surface. See, that's the one. See, you see the big, the nice gamma kick here. You get a nice gamma kick there, and you get a nice gamma kick there. So this was what Galloway, what intrigued Galloway, is the ability to do that. But the Exxon folks call that your maximum flooding surface, and the surface would be the surface of the condensed section, which is just below there, that surface. Once you recognize these sorts of patterns, it becomes relatively easy to sort out the stratigraphy from well logs. What I do, the very first thing that I do when I'm looking at a well log is I look for the highest gamma ray shale. That's most likely going to be your condensed section and maximum flooding surface. So if I go down a log, if I see 3 nice big gamma ray kicks, I say, well, there's probably 3 maximum flooding surfaces, meaning 2 cycles of sea level change, or 3 cycles of sea level change. But that's my correlation marker. So I don't correlate the top of sand or the bottom of sand for that reason. Let's see if I want to. Yeah, I guess I'll do this since some of you had to leave. I don't want to get started on sequence stratigraphy today. I'll kind of lead up to an introduction here. I've been talking about sequence and seismic stratigraphy. Okay, seismic stratigraphy, if we wanted to define it, we could use this definition here. Seismic stratigraphy is a related discipline that utilizes sequence stratigraphic concepts to interpret seismic reflection data in terms of the hierarchy or the stacking of stratigraphic units. And there are certain features that I'm not going to go into here, but certain features that you can look on seismic that allow you to develop these depositional sequences. It allows you to recognize them, and once you've done that, you can use one of these models like that to predict where within that sequence on seismic, where your hydrocarbon source rock will be, condensed section, where your most likely seal will be, that'll be the condensed section also, because it's very shaly and aerially extensive. Where are going to be your incise valleys and things like that? Well, they're going to be beneath the maximum flooding surface. And where's your high stand progradational deposits going to be? Above the maximum flooding surface. So you go to a seismic line and you recognize, let's just take this line, this one's been interpreted, but we'll say this might be a sequence boundary. this might be another sequence boundary right here, based on various seismic features that I'll talk about tomorrow, but I don't want to get into them without everybody here. And then this reflector down in here is probably your condensed section. See, so you can take your seismic, and once you can identify these sequence boundaries, you can interpret the geology or the stratigraphy within those sequence boundaries. Well, that's nice, and but I've been showing you a lot of pictures of horizon surfaces from 3D seismic. And here's an example. What you're looking at is some, what we call a horizon slice. You probably all know this, but say it anyway. A horizon slice, which is any slice of your seismic data. Let's just take this slice here, follow it down. That will have represented the seafloor at some time in the geologic past. Okay, that's going to be with the seafloor. So if there were a way to flatten that out and look down on it in a 3D seismic survey, you'd actually be looking at a representation of the seafloor at that time of deposition. So what one does is you take your horizon and you flatten it out. Once you flatten it out, you're now looking at the seafloor, with a representation of the seafloor at the time of deposition. Now here you see some very nice meandering river deposits. Okay, there's actually two of them here. There's one set that goes, if you can see this. There's one meandering river system. Well, it's not going to show up here. Let me do this. Okay, you've got one meandering river system that's coming down like this. And then you've got another one that's crossing like that. Where would just on that basis, where would you want to drill your well? I think if I had nothing else but this, I would select right here where these two cut through each other. You're going to get a thicker sand. Should I drill a well up here? Why bother? There's no sand up there. So you don't get that kind of information with 2D seismic, but you do with the 3D seismic just by flattening out these horizons, and then you're essentially looking at a representation of the seafloor. So in this case, you want to confine any wells to this area in here, or that area in there. And you see there's some nice point bar deposits here. Here's one there, there's one there, and so on. So doing this really narrows down the amount of work you have to do in your interpretation. And it gives you a much more accurate interpretation because you can actually get an image of what you want to drill. Can't always do that with the two-dimensional. Well, you can't do that with the two-dimensional. You can still interpret with the two-dimensional. You can still interpret where the sand might be over an area, but you can't pinpoint it like you can with the 3D model, with the 3D volume seismic. Now, there's another way you can look at these horizons, and that's what we call a seismic time slice. And what that is that's where you just go to some seismic horizon, some seismic time, and I think you all know that seismic is in not measured in depth, it's measured in two-way seismic travel time. And so you take one of those time intervals and just flatten it out like that. And then look down at the surface. Well, what happens when you do that is you're cross-cutting these stratigraphic boundaries. So you get a false image when you do a time slice as opposed to a horizon slice. You get a false image of your stratigraphy. Now, a lot of people use time slices for structure, and you can often see faults and things like that nicely on a time slice. But when it comes to working out stratigraphy, you want to do a horizon slice. Well, it's a little bit more complicated and more detailed to make a horizon slice than it is to do a time slice. So if you're only looking for structure, time slice will do the trick for you. I don't think I have any pictures of that to show you, but the horizon slice is what you want when you're looking at stratigraphy. Okay, I just want to finish up the day with just showing you a few. So let me back up to one of the points here. This has evolved into a very powerful science, looking at these horizon slices. And a lot of geophysicists in particular spend a lot of time trying to improve the resolution of the features that you see in these horizon slices. Geologists use it to see the geologic features, to identify the geologic features. So it's an area where geologists and geophysicists can work very closely together to sharpen up an image and then to identify what that image means. And then you can get the petroleum engineer in there, or the drilling engineer, as to where to drill your well. So this has evolved quite nicely into a pretty impressive and powerful science, and we call it seismic geomorphology. Word here, seismic geomorphology is a term that's been applied to that. Seismic geomorphology. Remember what I said to the Exxon folks when they came out in 1978 with their book. The book was called Seismic Stratigraphy. This was the name of the book. It was revolutionary at the time because it showed that you could detect stratigraphic features on seismic records. So you could use the seismic for things other than structural interpretation. But at that time, there was really virtually no 3D seismic, and it wasn't until 3D seismic became more commonplace that people started looking in these 3D surveys, looking at these horizons in there, and what evolved from that was the field of seismic geomorphology. Kind of the leader in that is an Exxon guy by the name of Henry Posmentier. He's the guy that kind of figured this out. Very interesting. I know Henry, and he's an excellent geologist, and he's equally as good an artist. And it's very interesting because it's the art part of him that was able to look at images and figure out how to best portray those images so you could maximize what you were looking at. So very interesting. He can spend hours over these seismic horizons, coloring them. There's programs now to tilt the horizon and have a sun shadow on it to kind of highlight features. There's all kinds of things like that. Okay, well, I'm going to skip through quickly to end the day, and I'm going to skip past some of these. But geomorphology is a word for earth forms. So seismic geomorphology is a term for depicting and identifying Earth forms based on seismic. Skip that one. Skip that one. This is one of Henry's designs where he's tilted the horizon. So it adds a sun shadow here. It'll put an artificial sun up in the corner so that the sunbeam is coming down like that, so you get a shadow effect. Even though that's a horizon, you get that sort of effect. Very powerful. What you can see here, you can see a nice submarine canyon here going out onto a basin floor. There's another one here. Here's a incised valley going across a shelf and forming a submarine canyon that goes all the way down to the seafloor. So you can see features like that very easily. Skip that, I want to skip that, skip that. I just want to really show you a couple of these pictures. Valleys, okay, the incised valley. How can you identify that on seismic? Well, I see it right here. Let me get a color there. Okay, incised valley, right there. See how that high amplitude reflection has been truncated by this valley, and you can see the shape of a valley, an incised valley. Remember when we were talking about meandering river systems, and I talked a little bit about these lateral accretion packages that kind of downlap, and they represent nice sandy point bars. Well, here's one in here. See that one coming down like that? That's what that is. Seismic representation of that. This is going to be your channel. What I'm coloring in now, this is going to be channel, which is probably going to be shale filled. And your sand is going to be right in there, where you get that nice point bar. Okay? So everybody likes to drill channels, you know. I've never met anybody who didn't like to drill a channel. And the reason is because they're usually easy to see. But the point is, you know, here you've got a channel that I just interpreted for you, and you want to drill your well in the center of the channel? Well, I wouldn't do that in this case. I'd be drilling my well over on this side where I've got a nice point bar sand. I wouldn't drill it on this side because that's probably going to be a mud plug, okay, when that channel became abandoned. So one can do this sort of detail, and in reservoir characterization, that's really what you want to do. I didn't talk too much about levees, but there's a levee deposit right there, coming down like that. So you can really do detailed interpretations if you want to take the time and once you tune your eye to what you're looking at. The crevasse splay, here's your main river here, and here's a crevasse splay coming off. That's on a horizon slice. Here's a crevasse splay. Remember I said yesterday these crevasse splays usually form in the outside bends of rivers. There's one on the outside bend of this river here. And why it's there is because during a flood, when these waters were flowing very quickly, around the outside bend is where you'd have your highest flow velocity, and so you breached through the channel margin and spilled the sand out right at that point where you get that bend in the meander. You've been through this quite a bit. Now there is one thing I can add from this. One thing I didn't talk about was the cross-sectional shape of meandering river deposits. It turns out that if you look at the cross-section of most meandering rivers, it'll be asymmetric. The cross-section will be asymmetric. This will be the cut bank side. It's cutting, so it's always a steep side. This is going to be the point bar side, which is always depositing. So it's going to be a lower gradient. And you get your lateral accretion packages over here. Well, can you tell me where you would want to drill your well? Here. What I see is, let me get a transparent color. I see an asymmetric channel right there. See, here's the shallow gradient side, there's the steep side. So where are you going to drill your well? Are you going to drill your well in the middle? No. You want to drill your well over here, the point bar side. That's where your sand's going to be. So these little things can mean the difference between a successful well and an unsuccessful well. Here's another one. Let's see, is that a, yeah. Here's another asymmetric point bar. See the steep side there and the shallow side over here. So again, I'm going to want to drill my well over here. That's where I'm most likely to find my point bar sand, on this side of the channel, not on this steep bank of the channel, the cut bank side. So if you're looking down at a horizon slice, you can tell where's the cut bank going to be and where's the point bar side. Well, the outside bend of the meander loop is going to be the cut bank side. Okay, because your river is migrating and coming around that bend where your flow velocities are highest. And then here's your point bar, and you can actually see a few of these little scroll marks here. So there's your point bar. So in this case, looking down, I'd want to drill my well right there, not over here.
Dr. Slatt, just out of curiosity, in that same picture where you're at right now, what would be that black mark at the bottom left of that picture?
This?
Yeah, looks like a point bar. No. In the next picture, the one on your right.
Oh yeah, there's another one here. In fact, this one's even
it looks like a point bar, but it's black, right? In the color.
You mean this one?
Mm-hmm.
Well, that's just an amplitude change. And it might represent a shale break in between, because down here, you've got a very nice asymmetric point bar, and you can even see lateral accretion packages. There's two of them. See the brown coming down?
Mm-hmm.
Brown coming down? Boy, that's... So now you've got two drilling targets. So we're going to put a well in here. It's going to be a really good well. We'll put our well right in like this. Well, I should have done it. Just can't draw very well. Ah. Okay, so we're going to drill a well that goes through this point bar and that point bar. So now we're going to hit two reservoirs. And maybe this black is probably a high amplitude, it's probably a shale that separated two periods of time where you had falling sea level, then early rise, you filled up your incised valley. Let me back up. Falling sea level, you carved out the valley. Turn around in early rise in sea level, you backfill the valley. Then you had a marine transgression, okay, the black line, and then you had another drop in sea level. You carved out another valley, and then with the rise in sea level, you backfilled that valley. So that's how I would interpret that. So you have two potential drilling targets. Now, if you were to drill straight down, like this, you'd probably miss them both by a little bit. Okay?
The last picture that you have in there, the last square, yeah, that one, right there, that bottom left corner.
What's that black thing?
Yeah.
I don't know.
Because but it looks like a point bar as well, right? If
Could
you
be.
look at the direction of the river.
Yeah, it could be because the river is coming down like this and coming around, I think.
Okay.
But I'm not sure what that is, yeah. It's unusual to see that sort of feature. Maybe it represents a super high amplitude or something, I don't know. But here you see the nice outside bend. That's going to be your cut bank side. Here's going to be your point bar side. Oh, that's where you drill your well. Well, that's probably a good place to quit for the day. We've now drilled, I don't know how many wells we drilled today, but we drilled a lot, and every one of them was a good well. Okay? How about that? So why don't we quit for the day then, and we'll start again tomorrow and talk about sequence stratigraphy. And what I want to do tomorrow is kind of put all of these into kind of all of these depositional environments into kind of a stratigraphic framework that you can use to predict where the sand bodies are going to be, where your reservoir bodies.
In that picture over there,
Huh?
the body we're looking at.
Yeah. Well, it's like, this is the way it is. It's asymmetric. Yeah, but we're looking at a cross section, yeah. Okay, steep side, that's the cut bank. Here's the point bar side.
Okay, but then your transgressional
Comes over the top.
this one.